Now let us explore now how to derive this equation. Okay, what is the mathematical foundation for this equation? We discussed about the logistic regression equation. This is what the logistic regression equation, the natural log of p over 1 minus p is equivalent to the beta naught plus beta 1 x1 and so on. Okay, so why we are taking the log on the odd? So that is what the question. And how did we first of all get this equation? That is what our question. See, I just derived this again. I'll explain you step by step. Okay, don't worry. Okay, for example here, right? So I just write this something like this exp of let's say beta naught plus beta 1 x1. This is enough. Okay, simple logistic regression because of space issue, right? I just write it like this, and then I'm going to put it in the denominator exp of beta naught plus beta 1 x plus 1. So what is this? Why do we need this one? We discussed two different issues in the yesterday session. For example, you are making a prediction, right? Let's say you are so stubborn, you still want to use the linear regression, right? So in that case, what will happen? If you make a prediction, the values go above 1 also. There are some cases the values can go below 0 also. The probability values are lying anywhere between 0 and 1. If somebody says, right, there is a 0.5 probability I will get height, there is a uncertainty here. He may get promotion or he may not get promotion. Right? Any value that is closer to 1, that means there is a higher certainty. If somebody says, right, there is a 0.8 probability that I can get shortlisted for the interview or, right, something like that. So in that case, the confidence level is very high. So in that case, right, any value that is closer to 1, that means the likelihood of happening that event is very high. Any value that is closer to 0, the probability or the likelihood of that event happening is very less. The chances are slim. Okay, fine. This is fine. So in the case of logistic regression, the values should be bounded between the predictor value is supposed to be bounded between 0 and 1. It should not be less than 0 and greater than 1. As we have discussed one scenario yesterday, I just go to that previous slide. Yeah, this is what I discussed this is the example I gave you. For example, in your linear regression, this is the one you want to predict, right? So the purchase, you want to predict the probability of purchase. On the right side of the equal sign, you can see the intercept plus the slope. The intercept and slope values were computed by the model. And this is the value we got it. Okay. So the only thing is, right, we need to multiply this slope with the age. The idea here is, given this age, any age, right, the model has to predict predict the probability that whether the customer is going to purchase or not. Here, whether the customer is going to purchase or not. Either yes means purchase, no means no purchase. In this case, we are predicting the probability. In this case, what happens? So, for example, a 32-year-old customer, what are the chances of a 32-year customer is going to purchase from us? So if you plug in the 32 year in the place of age, 32 into this one plus this one, you'll get 0.562, which means this is almost close to 0.60. The probability of a 32-year-old customer is going to purchase from our business is 0.60 almost. This is fine. What if a customer age is 48? If you multiply 48 with this value, and if you subtract the intercept from this, you are getting 1.778. So this is the problem here. What problem it has here? This is the problematic one. Because the probability value lies anywhere between 0 and 1. Should not be more than 1. This is an issue. Fine. Okay. Now let us take another customer whose age is 24. And if you plug in the age 24 here, the probability of a customer with the 24-year the purchasing probability is negative 0.046. This is also another problem. So this is good, but these two are not correct because the probability values are lying anywhere between 0 and 1, not above 1, not below 0. Here it is below 0, it is above 1. Using logistic regression, we have the sigmoid function. Look here, this is called your sigmoid function. What it does, this is the one squashes your value, any value between 0 and 1. Even though you have 1.778, this equation, what it does is it will squashes your value anywhere between 0 and 1, and then it will convert this negative value to positive value by taking exponentiation. Okay, by taking exponentiation. All right. Fine. So, okay, now the question is, okay, there are two issues here. The P is greater than 1 here. The probability is greater than 1 here. And the second one is the probability is negative. How do you convert the negative into positive? You can square the value, or you can take the modulus. But what they did, scientists, right, they have used exponentiation. Okay, you take exponentiation of this value. Okay, so in that case, what will happen is the negative value will go off, and then it will convert this value anywhere between 0 and 1. Okay, so this way they address this issue. Any value that is less than 0, for that, so for that they took exponentiation. And then how do you address this issue? One problem, we addressed it by taking the exponentiation. In this case, the negative minus will go away if you take exponentiation. Okay, so in this case, the value is more than 1. Here there is no negative, it is more than 1. What can we do? So for that, what they did, if you divide the same value by itself, for example, 1.778, and then if you add a small value with that plus 1, what will happen is it will convert this one, anywhere between 0 and 1. You just give any number, you try any number. For example, you have 256 and divided by 256 plus 1, it will convert the value anywhere between 0 and 1. This is what they invented it. Okay, so just keep that in mind. Okay, now I just go to that slide where I wrote that, right? So to obtain a probability, what they did, exponentiation of beta naught plus beta 1 ex1, like that. Okay, and then what they did, so 1 plus exp of beta naught plus beta 1 x. This equation solves those two problems. Like any negative value, it will get converted as a positive value with the exponentiation. And then if you divide the same value by itself, and then if you add 1, it will convert any value between 0 and 1, irrespective of the value that you get. You get 2.22 or 256 or 1 lakh, whatever it may be. It will convert, it will squash that value to fall anywhere between 0 and 1. Okay. So this is what they did. So now what I do is I'll just make it very simple. Instead of using exp, I just write e, and then e raised to the power beta naught plus beta 1x divided by 1 plus e raised to the power beta naught plus beta 1x. I just rewrite something like this. Okay, and then what I do is I take the denominator to the left side. Okay, so what will happen? Anything in the denominator, if you take it to the left side of your equal sign, it will become multiplication. So here what will happen is 1 plus, already we have p into 1 plus e to the power beta naught plus beta 1 x. Okay, we are left with only the numerator on the right side, e to the raised to the power beta naught plus beta 1 x. Okay, and then what I do is p into 1 is p plus p into e to the power beta naught plus beta 1 x is equivalent to this side. the beta naught plus beta 1x. Now what I do is I'll just keep only the p on the left side. And then if I move this to the right side, what will happen? It will become negative. E to the power beta naught plus beta 1x minus p into e to the power beta naught plus beta 1x. To simplify that, what I will do is e to the power beta naught plus beta 1x into 1 minus p. Got it? So what I'll do is the next step is I just move the 1 minus p to the left side. What will happen? It will become a denominator, right? So the p divided by 1 minus p. So this is 1. Okay, don't get confused. 1 second, or else I just remove this one. 1 minus p. And then on the right side, we are left with e raised to the power beta naught plus beta 1x. If you take anti-log on both sides, what will happen is natural log of p over 1 minus p. Since you are taking the anti-log, what will happen is the e will go away. We are left with beta naught plus beta 1x. Priya, can you see that? So now we got this original equation. This is how, this is the logical or mathematical intuition behind the logistic regression equation. Yeah, yesterday I did a different way. So that is the one will that is the one will help us to land with the sigmoid function. Okay, sigmoid function. What is sigmoid function? This is very, very important. Please remember this. The probability of y equal to 1 given that x is equivalent to 1 divided by 1 plus u to the power minus beta naught plus beta 1x. Okay. Instead of specifying beta naught plus beta 1x, what we do is 1 divided by 1 plus e to the power minus z. So here sigmoid of z. This is very important because this is called your sigmoid function. Sigmoid function. This is the one. It will be helpful to squash any value. It will squash any value between 0 and 1. Okay, this is the one. If you simplify this one, yesterday, if you see that derivation, I did that. Okay. So using that derivation, you can arrive the sigmoid function also. Okay. Got it? Okay. I started saying that how we arrived this equation. Yeah, to answer to that question, I have, I derived this. Hope you understood. And the yesterday's session was related to the sigmoid function. See, in the case of linear regression, we are fitting the straight line. In the case of logistic regression, the straight line will not work. What we do here, let's say we have zeros and ones. Zero means the customers are not going to purchase. One means the customer is going to purchase. So let's say there are some customers like 17-year-old, 18. This is, let's say you have age plotted in your x-axis, the 17, 18, and 22, and something like that. Okay, there are some, people, right? Customers, they don't purchase. There are some customers they purchase in the past. Let's say a 26-year-old guy he purchased it, and 28-year-old lady purchased it, something like that. You plotted the data, zeros and here, ones here. And in this case, if you draw a line here, this line is your predicted line. Predicted value lie on this, predicted values lie on this line. Hence, the actual and predicted value will be closer. Hence, the error will not be much. Okay. You join all this line, okay, all these dots, and then if you connect these two things, this is called your S-curve. The case of logistic regression, we are fitting the model with the S-curve. The equation for the S-curve is sigma of z is equal to 1 divided by 1 plus e to the power minus z. So this is the one you need to remember. The S-curve equation is this one. The case of linear regression, we know what is the equation for this regression line, y is equal to beta naught plus beta 1x and so on, right? So here, sigmoid is very much important. You need to remember this sigmoid function. Sigma is equivalent to 1 divided by 1 to 1 plus e to the power minus z. Yeah, you watch my yesterday's session, wherein I was about to arrive this one. Okay. So this is the one I arrived in yesterday's session, right? So if you simplify this, what will happen is, P is equal to 1 divided by 1 plus, instead of, this is the one, right? So this one will go away. If you factor out what will happen, this one will go away. The numerator you will have 1, and the denominator you have 1 plus e to the power, instead of beta naught plus beta naught, z will put it. Okay. So since it is in the denominator, 1 and e to the power minus z. So 1 divided by 1 plus e to the power minus z. So how did we arrive this one? So that is what I explained in yesterday's session. You can watch that video. You are clear with that, right? Okay, fine. But I did not discuss about the sigmoid function in the yesterday's session. Now I have clarified that. Okay, what is next? One second.